Imagine a programmer hunched over a desk, their screen glowing in the dim light. They've written a complex algorithm designed to analyze other programs, determining whether those programs will eventually stop running or loop indefinitely. Confident in their code, they test it on a simple script. It works. They test it on a more complex one. Still works. But when they input their halting detector into itself, a program analyzing its behavior, the system freezes, an infinite loop of paradox. The programmer realizes with a sinking heart that their tool cannot decide its fate. This is the essence of the halting problem, a question that Alan Turing posed in 1936, proving that no general algorithm can determine whether an arbitrary program will halt or run forever. It is a paradox that reveals an unbridgeable chasm in computation. Some questions are fundamentally beyond the reach of even the most advanced machines. The problem is unsettling not just because it defies solution, but because it exposes the fragility of our faith in technology. We assume that with enough power and ingenuity, computers can answer any question. The halting problem reminds us that certain truths are inherently unknowable, even in theory. It asks, can we ever fully trust an algorithm or ourselves to predict the future? The halting problem is rooted in a simple question. Given any computer program and an input, can we decide algorithmically whether the program will eventually halt or run forever? Alan Turing answered this with a definitive no, using a proof by contradiction. Here's how it works. 1. Assume the existence of a halting detector. Suppose there exists a program, halt, P(i), that takes another program, P, and input I as inputs. Halt returns halts if P stops when run with I, and loops forever otherwise. 2. Construct a self-referential program. Create a new program K, P, that does the following. Takes another program P as input. Uses halt, P, to determine if P halts when given itself as input. If halt, P says halts, K, P enters an infinite loop. If halt, P says loops forever, KP halts. 3. The contradiction. Now run KK. That is, let K analyze itself. If halt KK says halts, then KK must loop forever by its design. If halt KK says loops forever, then KK must halt. In either case, halt's prediction is wrong. The contradiction proves that halt, P(i) cannot exist. The paradox arises from self-reference, much like the liar paradox, segment 12, or Russell's paradox, segment 14. A program analyzing its behavior creates a logical loop that cannot be resolved. Turing's proof was revolutionary because it showed that undecidability is a fundamental property of computation. Even in theory, some questions have no algorithmic answer. This is not a limitation of current technology, but a mathematical certainty. The halting problem is the cornerstone of computational theory and has far-reaching implications. It implies that no universal debugger can exist, a tool that guarantees to find all infinite loops in any program. It also means that certain questions about programs, like does this code contain a bug that causes it to run forever, are unanswerable in general. Exploration of implications. The halting problem is more than an academic curiosity. It reshapes our understanding of computation, ethics, and the boundaries of human knowledge. 1. The limits of artificial intelligence. If a program cannot predict its behavior, how can we trust AI systems to act safely or ethically? An AI might optimize for a goal, but enter an infinite loop of unintended consequences. For example, a self-driving car's algorithm could theoretically get stuck in an infinite loop deciding whether to swerve or stop, a scenario with real-world stakes. The halting problem suggests that even superintelligent AI will face inherent limits, unable to guarantee its actions. This raises ethical questions. Should we program AI to avoid self-referential tasks or accept that some risks are unavoidable? 2. Gödelian reflections. The paradox parallels Gödel's incompleteness theorems, segment 12, which showed that mathematics cannot prove its consistency. Both reveal that systems, whether logical, computational, or mathematical, cannot contain or fully analyze themselves. Just as a mathematical system cannot prove its completeness, a program cannot analyze its halting behavior without contradiction. 3. The illusion of control. The halting problem underscores the limits of human control over technology. We might strive to create foolproof systems, but Turing's proof reminds us that some risks are irreducible. This is a humbling truth in an age of AI and automation. Even with infinite computational power, certain questions remain beyond reach. 4. Practical implications in computing. While the halting problem is undecidable in general, programmers and engineers work around it using heuristics and approximations. For example, compiler optimizations. Tools like linters can flag common infinite loop patterns, e.g., loops without exit conditions. Runtime monitoring. Systems can terminate programs after a timeout, but this is a practical workaround, not a solution. Formal verification. Techniques like model checking prove correctness for specific cases, but cannot handle all possibilities. These tools acknowledge the halting problem's existence while striving to mitigate its effects in limited contexts. 5. The ethics of unpredictability. The paradox challenges our moral responsibility. If a program's behavior cannot be fully predicted, who is accountable when it fails? For instance, an AI diagnosing medical conditions might sometimes loop, indefinitely delaying treatment. The halting problem implies that programmers and developers must accept a degree of uncertainty, designing systems with fail-safes and probabilistic safeguards. 6. The comfort of incompleteness. The paradox offers a strange reassurance. Perfection is not required. Just as mathematics thrives despite Gödel's incompleteness, computing can progress by focusing on solvable subsets of problems. The halting problem does not mean all programs are unpredictable. It means we must prioritize clarity and simplicity in design. 7. The philosophy of computation. The halting problem asks, what does it mean for a machine to understand itself? A program analyzing its own code faces a mirror, reflecting the same limits humans face when introspecting. This parallels the Sorites paradox, segment 11, where boundaries of understanding are fuzzy, and the liar paradox, segment 12, where self-reference breeds contradiction. 8. The illusion of omniscience. The paradox dismantles the myth of computational omnipotence. Even with quantum computers or neural networks, some truths remain beyond reach. This humility is critical in an era where AI is often portrayed as all-powerful. 9. Connections to other paradoxes. The halting problem is a cousin of Russell's paradox, segment 14. Both involve self-reference and show that systems cannot fully contain or analyze themselves. Just as set theory needed new axioms, computing must accept inherent limits. 10. The cosmic scale of unknowability. The paradox mirrors broader existential limits. If we cannot predict all program behaviors, perhaps we also cannot predict the full consequences of our actions or the universe's fate.
The halting problem asks, can a program ever know what it doesn't know? The paradox of choice asks, can a human ever choose what they don't want? Imagine standing before a menu with infinite dishes. Each choice feels appealing, yet indecision paralyzes you. This is the paradox of choice, a psychological quandary where abundance leads to dissatisfaction. Like the halting problem, it reveals that limits are not flaws but necessities. A program cannot decide its own fate. A person cannot choose among infinite options without anxiety. Both paradoxes frame human and machine alike as beings of bounded rationality, navigating a world of endless possibilities with finite tools. The halting problem's contradiction is algorithmic. The paradox of choice is emotional. Yet both whisper the same truth. Too much knowledge or freedom can become a cage. As we turn to the paradox of choice, we shift from the limits of computation to the limits of human happiness. The halting problem says that some problems have no answers. The paradox of choice says that some abundance has no joy. Together, they frame existence as a dance between what we seek and what we can grasp. This expansion weaves the halting problem into a meditation on computation, ethics, and the human condition. It avoids bullet points by using narrative and philosophical exploration, maintaining the reflective tone. The transition bridges seamlessly to the paradox of choice by contrasting computational limits with human psychological limit.